Well, welcome to our Wigner Lecture Series. I'm filling in for Tom this morning, and welcome to our lecture series and our talk by Sir Harold Kroto. He tells me that he wants to be introduced as Harry, and so I'll introduce him again as Sir Professor Harry Kroto in a few minutes. I want to introduce some special guests that we have. David Milhorn, Executive Vice President of the UT system. I walked over with him, but I don't know where he landed. David, if you will just maybe, there he is, right over there. Raise your hand. Thank you for coming. Our lecture today is being recorded for later viewing. It's not being streamed, so we are going to record it so that people can click and take a look at it later on. About the lecture series, we started this lecture series in 2013, in November of 2013, and we've had quite a few really good lectures and many Nobel laureates. The lecture series is organized by our corporate fellows, and the goals of our lecture series is to invigorate scientific discovery, spur technological innovation, and initiate productive scientific policy debate. The lecture series honors Eugene Wigner. He's the patron saint of ORNL. He was trained as a chemical engineer, and he won the Nobel Prize in 1963 for atomic theory. He was the founder of the field of nuclear engineering, and he's a role model for coupling of basic and applied energy work, which we do here at the laboratory. He was the research director of Oak Ridge, which was then called the Clinton Labs, back in 1946 to 1947. Wigner led the broadening of our lab mission to nuclear R&D, the reactor engineering and effects of radiation on materials, associated chemical, physical, and life sciences, and, very importantly, education and training. Today, our lecturer is another Nobel laureate, Sir Harold Kroto. He's recognized by the Nobel Prize in 1996 for the discovery of fullerenes, what we call Buckminster fullerene, and he shared the prize with Robert Curl and Richard Smalley. He has a distinguished career in the fundamental areas of chemistry, early work in spectroscopy, discovery of the first chemical compound containing phosphorus-carbon double bonds, and of a new class of long carbon chain molecules. Later studies of the physical-chemical nature of carbon vapor with Smalley, Curl, and others at Rice University ended up in the discovery of Buckminster fullerene, or C60. His current research interests are cluster chemistry and nanotechnology, including investigations into molecular mechanisms of fullerene formation. He's also dedicated to communicating science to the public. He's co-founder of the Vega Science Trust to provide scientists with broadcasting platform for this purpose. In 2001, he received the Royal Society's Michael Faraday Award, given annually to a scientist who has done the most to further public communication of science, engineering, or technology in the United Kingdom. He's the driving force behind the Global Educational Outreach for Science, Engineering, and Technology, Geoset. And its purpose is freely accessible educational material online. One of Geoset's sponsors is the Kroto Research Institute at Sheffield University, where Sir Harold completed a bachelor's degree of science and chemistry and a PhD in molecular spectroscopy. He claims to have stayed on for a doctorate in part because of an intense and continuing interest in art and graphic design, pursued in parallel with his scientific research. In 1994, he received the Moet Hennessy Louis Vuitton Science pour l'Art Prize for his graphics and arts work. He had a postdoctoral research experience at the National Research Council in Canada and in the Bell Labs. In 1967, he joined the University of Sussex and now is emeritus faculty there. Since 2004, he's been the Francis Epps Professor in the Department of Chemistry and Biochemistry at Florida State University. He has 29 honorary degrees and many other awards, including the Longstaff Medal, the Royal Society of Chemistry in 1993, the Autologous Prize for Innovation in Chemistry in 1992, Fellow of the Royal Society in 1990, Faraday Lecturer in 2001, and Copley Medal recipient in 2002. He's been on the board of scientific governors at the Scripps Research Institute, a foreign associate, U.S. National Academy of Sciences, Knight of the British Empire in 1996, and we're very fortunate to have him here today to lecture on the topic of carbon in nano and outer space. Please welcome Sir Harold Kroto.
Well, just to check, you can hear me okay at the back? Yeah? Put your hand up if you can. If you can't, all right, I hope you can. I'll shout as much as I can. It's a pleasure to be back here. I think it's some 97 or 98 when I was here before. Anyway, just to tell you, I had a life before C60, believe it or not. Lecture in chemistry in nano and outer space. And there we go. Okay, well, what was it? Well, believe it or not, I was not always as old and decrepit as I am now. Believe it. And I was younger than most people here. And I didn't want to be a scientist. What I really wanted to be was Superman. And I have proof of this, because here it is. So I did other things. I couldn't be Superman, gymnastics, and played tennis for the university. And I acted in a play, Henry V. And I blow this up. I'm the handsome guy on the right, in case you don't recognize me anymore. But the guy in front became an actor. And I tell young people, and there are quite a lot here, don't become an actor, because he is now 5,000 years old. And I'm slightly younger than he is. Okay. Anyway, I ended up as a scientist. Ian came out to stay with us for a few days in Tallahassee. And of course, I had to take him to the mag lab. I told him in his little finger he has more magnetic field than in all this great thing. He should come here and sort out your fusion problems. Okay. Okay, here he is with that. Anyway, yes, well, what did I do? I did molecular spectroscopy, and we observed these molecules by microwave and photoelectron spectroscopy, the first carbon-phosphate double-bonded species, and then we worked out how to make triple-bonded species, and then went on to some analogs of those, such as the boron sulfides, which are shown at the bottom. And that was a great time. Every few days, a new molecule would turn up. But the ones that are important for this talk are the ones at the bottom. But I want to show you my favorite molecule. It's not actually C60. It's this guy, because it looks like this. And can you see what it looks like? What do you think? A dog, yeah. It's my dog made of atoms, carbon, hydrogen, the red nose. And it's a very clever dog, because if you look at the microwave spectrum, you find that the dog shakes its head and looks at its tail. And then, not only that, the dog really is quite clever, because it can undergo internal rotation. It's been drinking. Is this a wet state? I don't know whether it is. But if you've been a dog and you've been drinking, you know what you really desperately need is a lamppost. Now, the reason for showing this is not just to make little kids happy, but to remind you that perhaps one of the most important aspects of molecules is that they're flexible. Carbon dioxide is not a greenhouse gas because it's carbon dioxide, it's because it vibrates. That's the crucial thing. And I think nanotechnology is not just building these architecture, but utilizing the dynamics of these molecules. Okay, I want you to remember that. Well, I was interested in the vibrations and rotations of molecules when I was a research student. And then when I went to Sussex, I was still interested in the quantum to classical picture of this. And the spectrum that started the ball rolling was this one, with my friend and colleague, David Walton, who had developed a technique for stringing carbon atoms together. He had made a chain of 32 carbon atoms, and that this was really beautiful piece of work. And the way he'd done that was by a copper-catalyzed oxidative coupling, where you basically couple them together like a train, okay, using oxygen. Okay, the molecule that we made was this one. It was made by an undergraduate. At the same time, some very exciting breakthroughs were made in radio astronomy, and particularly that one, which is the tallest at the bottom, Sagittarius P2. And we had made a molecule with 5 carbon atoms, and the one with 3, which is well known, had been detected. And my friend Takeshi Oka, who was a colleague postdoc in Canada, was working on radio astronomy with some astronomers in Canada. And I said, I've got this molecule, are you interested? And he wrote back and said, yes. He said, I'm very, 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 very much interested in your molecule. The same number of berries as there are carbon atoms. It's a good thing it wasn't 32, because there wouldn't have been space on the paper. However, we got together and we used this telescope, which you can see is a telescope in Canada in the middle of summer. And if you've lived there, you know what I mean. It's a 46-meter dish, and you can walk inside. That's the detector was the prime focus in this case. And if a molecule is rotating, can give out a photon, and you can detect it with incredible accuracy of 1 part in 10 to the 7th in frequency, maybe even better, depending on how cold the cloud is. Okay, so what we detected were these molecules in a small bit of, in this case, Taurus. The first one was detected in Sagittarius B2. And that was a very exciting time. We'd done the Foster compounds, and then we detected these carbon chains, and I thought those were two nice things. About that time, I thought, well, it's nice to have done two really quite useful contributions. It would be nice to have 3, because that's a round number. Now, I don't know why 3 is a round number, 2 isn't, but nevertheless, 1 more. And so anyway, what happened then? Oh, well, we were so excited that we sent it to the newspaper. Oh, security alert. Oh, dear. Oh, Ridge. Yeah, everybody move out of here. Okay. Okay. Well, we had our picture taken. Lorne Avery, Takeshi, Norm Broughton, and John McLeod. And here I am. I used to have some hair. Okay. It went to the newspapers, and it said they've discovered proof that there are organic chemicals in the vast dust clouds between the stars. Only one simple step would be needed to change these chemicals into the building blocks of life. You're only one step on from 5 carbon atoms. Anyway, that's the newspaper. But it went on better. The chemicals were discovered thanks to Canadian work in radio astrology. The Canadian astrologers, we're the researchers at Sussex. Okay, that's the newspapers. Okay, I'm sure you know something about it. Well, that was very exciting. And about the same time, a fantastic star was detected, IRC plus 10216. And that star, you can see here, well, you can't see the star. That's a forward scattering, and that's something about the size of the solar system, which is dust carbon chains were detected in that star. Now, tell you a little bit of what happened next, okay, hopefully. About Easter in 1984, Bob Curl invited me to Rice University. And he said, you should go and see what Rick Smalley's doing. He's doing something interesting. And here is Rick on top of this massive piece of apparatus. Not quite as big as some of the things here, but big enough to impress me. And as he was telling me what he was doing, which was to vaporize metals and silicon carbide to make clusters, it was on a Friday, and I was watching this, and I thought, well, if we replace the aluminium by carbon, maybe we can produce the carbon chains and simulate the conditions in the star. That's just it. Just vaporize the carbon, not metals, and maybe instead of clusters, we'll get these carbon chains. Anyway, about a year and a half later, Bob Curl rang me up. He said, we're going to do this experiment. Come over, or shall we send you the data? Now, here's a bit of the take-home message. I went there, okay? Within 3 days, I was there to do this experiment. Met Jim He, Sean O'Brien, and Yuan Liu. Now, Yuan, I'm sure, is somewhere. Where are you, Yuan? Yeah. Stand up. Okay. Yeah. Yuan was the first person to write in the book that C60 is very strong. Okay. So anyway, it's a long story behind that. So it's great to see Yuan and come back and see her again. Anyway, what did we do? And I think Yuan was working on the computer and produced this fantastic spectrum. Because there was a problem, because we couldn't print it out at first, okay? And Yuan was working behind the scenes to try and do this. And as you see, I wrote C60 plus question mark on there. Didn't know what it was. And it's off scale as well. And repeat this, C60 huge and C70 also. And we went to this particular restaurant, good company, and we sat at this table. Unfortunately, when I went back to try and find the pieces of paper on which we've been drawing what C60 might be, they'd cleared the table. So the doodling is gone. Well, we had graphite, and that was vaporized. And I was staying with Bob Curl, and I thought I'd show you the floor of his loo, or the washroom, because I would sit and contemplate this floor. What was so special about it? Now, the point about it is that C60 is not special. You can sit there all day, but you will not see the number 60. And you're looking for patterns. You understand, as scientists, you know there's something special about 660, and it's got to be a pattern of some sort. But that's flat. But it turned out that in 1967, I'd been to Expo, and my interest is not just in science, but in graphics. And I had taken Graphis magazine ever since number 103, and there was a special issue on Expo 67. And there was an image in there which, once you see it, it's spectacular. It's Buckminster Fuller's Dome. And Margaret, who's here, and our little boy, who was little then, we went into this. And once you've been in there, you sort of remember it. And the point about it is also that I'd made something for my kids. It was a star dome, which was, it was so many years beforehand that I couldn't quite remember. But I did remember that it had not only hexagons, but it also had pentagons. And whilst we were sitting there, I said, you know, this thing that I've got might be the right shape, but it's got pentagons as well. And that night, Rick was cutting out hexagons, and nothing spectacular happened until he remembered the pentagons. He put those in, and it magically closed up and came in the next day with this beautiful model with 60 carbon atoms. At that point, we were just totally bowled over. And then we discovered it was a football. Now, I want to show you a football, just in case you think, this is not a soccer ball, this is a football. We play football with our feet. I'm not sure what you play your football with. Unfortunately, many with your heads, which is a bit of a problem. Anyway, what we discovered is that we produced, by vaporizing it, simply vaporizing it, C60 molecules. And we had our picture taken, which is shown here. Okay, 1985, I decided something then that I was going to spend the next 5 years either proving that C60 was correct, but if it wasn't, I wanted to be the one to prove that it wasn't right. I didn't want anyone else to shove it down my nose, because we'd only got the number 60. We conjectured that it was this. I think we were a bit brave, but some points you have to have the courage of your own convictions. When you've seen it, when Yuan had put out these fantastic images with his song scale, it had to be something special. Okay, long story of 5 years, but then we got back onto this. I actually drilled a hole in one of these evaporators a year or so after that and made a big mistake. We vaporized graphite, and I thought it would be such a small amount of C60 that I needed a mass spectrometer to see it. That was a big mistake. There was so much in that. I had it basically sitting in there for a year or two, trying to get a mass spectrometer to monitor the situation. Anyway, we got onto this by Kretschmann and Huffman, who had done the same experiment, and we went back to that. And here Jonathan Hare at Sussex is manipulating the electrodes. And one day, he put this on my desk on a Monday, a red extract. And I was looking at this. This is just graphite, discharge, and it was soluble in benzene, 6th of August. During the week, we tried to do a mass spec on that. Friday of that same week, at 12:05, well, an hour before, and I got a call from Nature. That's the journal. And they... yeah, all right. they said, would I look at this paper? You don't see a hurricane coming. We don't have the computer capability you have here. Black Friday, 5 days after, this paper turned up from Nature, solid C60, a new form of carbon. As I read through it, there are fantastic images of these benzene, crystals out of benzene. And of course, it's C60. And as I read through, a wine red to brown liquid. Oh, shit. Red extract. Well, there you go. Go for lunch or commit suicide. Okay. Well, I don't know what it's like here, but lunch at Sussex is a bit like committing suicide. But anyway, we then realized that we'd actually done this experiment 2 or 3 years beforehand, and I hadn't been able to get a mass spectrometer. I'd done other things, but anyway. For me, the holy grail was a single-line NMR spectrum. A molecule with 60 carbon atoms with one line, you could prove it to be C60. Okay. So Tony Avent sent to this, I said, come down, I've got a fantastic thing for it. I looked at it, wow, that's benzene. He said, there's only one problem. He said, that's benzene. That's been done. But if you look here, what's that? That miserable little line is the first NMR spectrum of C60. I love it. Only a parent can love an ugly duckling like this. But that was it. It's one of my favorite results. And Roger Taylor worked out how to chromatographically separate C60 and C70. And we got the NMR spectrum of these here. And here is the Sussex team, which actually did that work. So we had a little bit of a nice time at that point. Okay, so that's a bit about the discovery of it. And let's go to here and bring this down. The name, well, what happened then is we were writing the paper. And I wrote the first draft, and then Rick went to finish it off. And he was sitting at the computer. He said, what are we going to call it? Well, for me, Buckminster Fuller had been a key. We got his book, actually. And I said, well, write down C60, space, Buckminster Fullerene, off the top of my head. And he typed it in and then forgot about it. And so that's how it happened, just on the spur of the moment, because Buckminster Fuller's dome and also the book, which we got to try and understand what was going on, was important in trying to decide what it was. Then there's a whole load of Fullerene chemistry, about, I don't know, maybe now 20,000 papers on Fullerene chemistry. I want to show you something about science as well. This is not just some of my students are Roger Taylor's and Dave Walton's. I only ever had a team of 2, 3, or 4 people. But look, we are an international brotherhood and sisterhood. That makes us different from everybody else on the planet. Because whatever we say, it has to be true in Japan, Argentina, Syria, Mars, and other places. That makes us different. We are 1 or 2% of the population. And if you want to know why there's a big problem today, because the 1, 2 to 5% of the population who made the modern world are outnumbered by 95% of the people who don't know what the hell is going on. But they use the technology, they use their mobile phones, and they don't care a damn about what's going on. And that's a big problem, it seems, today, because we have created this easy life where you can go to McDonald's for your food, you can switch the television on, get your beer, and you don't have to know what the hell is going on. And if you wonder why we got a problem, that's it. Anyway, 2004, I went to Florida State, and here is part of the team. The Steve who came from the UK, Daryl Artries, Prashant from India, Nicola Visitor from Italy, Paul Dunk. And this guy, well, this is actually Wigner's brother-in-law, believe it or not. And you know, he never comes into the lab. He stays out there all day long. Paul Dirac was at FSU, and his wife was, I think, Wigner's sister. Anyway, there you go. So I put my hat on him to keep him in the shade. All right. Margaret and I have had some wonderful 10 years at Florida State, some of the best years of our life. And what we've been doing is, I suppose, nanotechnology, chemical self-assembly. It's really 21st century chemistry. Would it be possible one day to create a computer by bottom-up chemical assembly? Well, obviously, because it's already been done. Your brain is some sort of computing, it's some sort of machine, right? It's already been done. In there, you can do things that that supercomputer cannot do, okay? So it's possible, it's been done, and in the future, hopefully, we'll do even better. All right, that was the thing. So what prompted me when I first went there? Well, I thought one of the nicest things was something I could see. You know, I don't know what the hell's going on inside the computer, but I could see this, okay? These first Farad cards, they're beautiful. They were made by hand, okay? And basically, you sent half the current through one of those and the other half through there, and you magnetize this. And I thought this is an interesting thing. Can we simulate this with nanotechnology, okay? Well, we went on the first rung of a 1,000-rung ladder because we made some nickel, or Prashant did, together with myself, Naresh Dalal, and Tony Cheetham, and we made a two-dimensional array of nickel clusters. They're not magnetic, but this is the start. Can you make a two-dimensional array of magnetic metal clusters? You should be able to do it. Addressing it is another matter. That was the start. But like all good students, they go off in their own direction. And Prashant went off into three-dimensional stuff and never came back. Well, I'm an old guy, 2 dimensions are good enough for me. However, that's what we were aiming at doing, but we went on to some other things. Here's Prashant, Naresh Dalal, Tony Cheetham, who were my colleagues on that particular project. Now I'm going to say a bit about science. When I was a kid, my name was not Kroto, it was Krotoshina. My parents were refugees from Berlin in 1937, and I was born in England in 1939. And then when I was about 14 or 15, my father cut the name down because people in Bolton, Lancashire, were unable to say Krotoshina. They could say Thistlethwaite, Entwistle, Ramsbottom, Higginbottom, and various other things, but Krotoshina was a bit more difficult. Basically because they never heard it. Anyway, Miss Bowker, who was 7 years old at the time, thinks I'd better write and tell you that we are not at all pleased with the way Harold, that's me, has been working during the last few weeks. He said, he is very fond of play. Well, that's interesting. I want to say something about the C60 experiment, and that it was the least important experiment I think I ever did. I was interested in myself, but it was just to try and prove that maybe when you vaporize carbon, you can get the carbon chains. I don't think it would have got me the money that was required to do the experiment and build this apparatus. And I think you want to really understand what fundamental science. Fundamental science is the science where you do things because you're personally interested in this and not running after the way everybody else is running. I only do things that interest me. And I'm now back on C60 because nobody's interested. They're all on graphene and nanotubes and stuff. And I've got the whole C60 original experiments, which Yuan will remember very well, all throughout myself. So Yuan, if you want to come back, you can do. Wow moment. What's science about? Well, about 1.5 years ago, we were in the town of Delft. And I was at a conference with Margaret, and Margaret was taking these pictures. And I was sitting at this table, and little children were coming to that table with a buckyball and say, can we have one? I said, you can have it if you can make it. This little kid, his tongue never went in, okay. Margaret took these beautiful pictures. And his sister wanted to make one, so she made one. These are very young children who can make this, no problem. I've seen 8-year-olds who couldn't do what these little kids could do. The first customer, however, that Margaret photographed was this one, 3 years old. And I want you to watch this. She was told to make 12 red pentagons and then join them together, as I say, with the white ones. And I've had 9 and 10-year-olds who could not do what this kid was able to do at 3 years old. She just watched the concentration of this. He assembled it, no help. She just seemed to know instinctively what to do, okay? Now, those pictures I just think are fantastic. But it turned out that when we looked at the photographs at the end, we didn't realize what we had. What Margaret had taken was the most amazing picture of all time. But look at that. That is a 3-year-old. You can't script it. You can see the absolute pure joy of creativity and producing something beautiful that they've done themselves, okay? That's what science is about. I don't think Margaret will ever take a more beautiful picture, but she's trying, okay? Okay, now here is the thing. Now, the reason for showing you that, I was playing around with the models, like this little boy, and trying to make C32. And when I counted up what I got, it was C28. And my hair stood on end because we got a signal with C28 very strong. So C28 took over from C60 for my personal favorite, because I made it on a Sunday afternoon, sitting at the coffee table, just playing around, again playing around. And I realized that it should be tetravalent. By putting 4 hydrogens on these carbon atoms, it should stabilize it, because it would still leave the benzene, the aromatic rings there. And I thought it'd be a superatom. And it seems to be one. About a few years later, Rick's group found that uranium could go on the inside, and uranium is tetravalent. And we've been putting titanium, uranium, and zirconium on the inside as well. And look at this. This is the most recent results. When you vaporize uranium in the presence of carbon atoms, the major peak, like C60, is uranium C28. There's some special relationship between uranium and C28, okay? And that's really quite interesting. We've also been looking at endohedral, and this is with Paul Dunk and Alan Marshall. And with potassium, C60 and C70 are special, okay? So with group 1, the metallofullerenes, no surprise. But if you put calcium inside, you get something that looks a bit like Batman, and C50 becomes a prominent species. And if you put group 3 metals, okay, scandium, such as scandium, N44, and with tetravalent, it becomes C28, which I've shown you. So there's some interesting things going on there, which we still don't quite understand. That's with Paul Dunk, Chris Hendrickson, Nathan Kaiser, Nori Shinohara, and Alan Marshall, who created this fantastic resolution that we have at the Mag Lab. We can separate anything, okay? In fact, he has separated a sample with 105,000 different molecules in it, okay? Okay, well, that's a little bit. Now, what I want to talk to you a bit about nanotechnology again, which is what is it, okay? Because I don't think people understand it very well. It's not just little things. One thing I was interested in quite a long time ago was the mechanisms of nanotube formation. And my thought was that if you looked under a microscope, you might be able to see this. Basically, what we see are closed sections. We're looking at the cross-section, basically, of a nanotube. And the central core is sometimes filled by a metal particle. And I was wondering, well, if you looked at, could you produce these little igloos? And my idea was that surface reconstruction of a carbide would cause a graphene sheet to come off, something like that, okay? That was a simple idea. In the case of nanotubes, which were created by by metal catalysis. Now, my colleagues Mauricio and Umberto Terrones, working with Florian Banart, came up with a beautiful result, which is shown here, and we'll show that again, looking at the cross-section under the electron microscope. Now watch this. You have a flat meniscus. It's curved, and then a line on the top. That's a graphene sheet coming off the top of it, and waves of these, and you see the birth of a nanotube. And possibly it might be shown here as well in real time. This is at 600 degrees in an electron microscope, where you're going to watch the birth of nanotubes, okay? You saw it here. This idea of probably a surface reconstruction is probably quite correct. Okay, so that's that, and now what I want to go to is what I think is the holy grail of nanotubes, okay? Oop, sorry about that. Close that. These things come out. There, okay? Now, this is what you should be doing, okay? Perhaps the ultimate material is this. Single or double-walled nanotubes, all the same, exactly the same diameter. If you think of this as a box of paper straws, okay? Stick them together with a weak glue, okay? Maybe post-it glue. Perfect hexagonal packing. And it will be interesting. You can stand on it, and it will hold you up. Paper straws, okay? Now, nanotubes already have the glue, van der Waals forces. So what we need is a bundle of 10 to the 15, okay? About an inch in diameter. Why is that? Well, we've got 20 here. There's a double wall from Endo in Japan. It will be effectively 100 times stronger than steel, 1/6 the weight. Why? Because a defect, which is the limiting factor in all materials, will not propagate to the next one. And you may even be able to anneal those out of there. So in one dimension, you will do what trees have known since time immemorial, how to make it strong, at least in one dimension. And that's the way forward. Can we do it? I don't know. It's possible, but probable, I don't know. We've a long way to go. Defects will not propagate. That is nanotechnology. It's not a little thing. It's taking advantage of something at that scale that is not there at the highest, at other scales. Flexibility, vibrations, and stuff like that. That's the challenge for you guys. I don't know. Well, C60 was wandering, okay? And I think we don't do enough wandering at the moment. Let me show you. I started off with this magazine, Graphis. I wandered into Sheffield Public Library in 1958 and discovered this magazine. I was curious about vibrations of long molecules, and that's why we made the carbon chains. David I met, and he developed this coupling reaction. Then that led to detection of carbon chains in space by radio astronomy, okay? And then we discovered them in stars. This red giant was discovered and the carbon chains were found in it. Bob Curl invited me to Rice and said, go and see Rick, he's doing something interesting. Another reason for going to Rice in Houston was half-price books. It's not just science. There was an ulterior motive. I really liked half-price books. Met Rick, suggested that aluminium, change it for graphite. Simulate the conditions in a star. Met Jim He, Sean Vine, and Yuan. Okay, C60, big surprise. Couldn't predict it. The clue for me was in Graphis, that picture. The red solution, my colleagues, and somehow C60, discovered by simulating chemistry in stars. It was not discovered by going after it, okay? So that's the take-home message. All right. Now, I want to say a bit of what I've been working on recently and about education, which I think is extremely important. I set up the Geoset program a few years ago. We use a computer, capture station, capture the video and the PowerPoint, okay? in dual window presentation, downloadable in the future. Basically, that's basically the situation. So I don't need to go now, and many of these are on the web. Now, I want to show you, oops, daisy, what our students are doing.
Here are the Beatles. George, John, Ringo, and Paul. We all know their music, and most of us even know of their impact on the world today. However, whether we realize it or not, we've had more contact with another type of beetle, and they have had far more influence on our very lives. And I'm talking about these beetles, the insects. And this presentation will be all about the wonderful world of beetles. So why talk about bugs? They are able to adapt to their own specific ecosystems and environmental niches. But can evolution explain beetle helmets?
I'm going to stop it there because I want to show you a few other people. Okay? What's this? Oh, the wrong one. That was an undergraduate, and our graduate students are making presentations.
Chemistry that we ourselves use, it's able to go through and transform it into these beautifully complex and beautiful flowers that you can see here. Now, what we do is much the same. We'll take something relatively small, something relatively simplistic, and through a series of transformations, we need to figure out how to make something that's much larger, much more complex. And that's the goal of organic chemistry, is to go through and try to find this bridge between these two things, to try and take different molecules and piece them together. You know, that's fun, that's nice. Why do we actually want to do this type of chemistry? Well, these structures that you see now on the left-hand side are used as what's called molecular wires or nanowires. And these are very, very good at going through and conducting electricity.
I'm going to stop it there because these now is a revolution. I mean, here is, whoops, I will show you this one.
Hey, my name's Daniel. My friends call me Dan, and other people call me other things. But we won't talk about that. Today, we're going to talk about color. So, you guys in the audience there, tell me, what do you think color is? Yeah, I see some ideas. Yeah, you in the back with the shirt and the pants. Yeah, you. I bet I know what you're thinking. I bet you're thinking that color is actually a bunch of little tiny aliens flying all over the place in little ships and shooting bits of color at our eyes all the time. No? No? Okay. Well, if you had thought that, I would have been like, mathematical. That's a really imaginative idea. I really like that. Because it turns out that color is even cooler than that. I know watching me on has light coming from it. But what is light? We're actually constantly being pelted by photons all the time. Kind of like that. And the photons will either bounce off of things or be absorbed by those things. And these are two processes called absorption and reflection when the things bounce off. So, we're not actually being bombarded by just one or two photons at any given time. It turns out that we're actually being hit by millions and millions of photons at any given time. Kind of like that.
I'm going to stop it there because this is a medium where our students can be creative, okay? But it's better than that. What we've done is we've revolutionized the resume. Instead of a pile of paper like that, which I think some of you have seen, you can actually watch someone like Kerry making a presentation. And you can see that he could be a good teacher, okay? So that's, and what's more for assessment, marking and stuff like that, which is a headache, I know. Here I am marking my students, drinking a glass of wine at the same time in England, okay. So I want you to think about this because this is the future. And with scientists, I want some evidence, okay? Kerry got a Fulbright, who you've seen, okay? We put the URL into their job application, their postdoc applications, their prize and award and things of this nature. Steve got us a Rich Media Award with a beautiful little presentation on Geoset. Prajna was the first student By return, she got a postdoc at UC Santa Barbara. She got 4 tenure-track offers, and then she wrote last year to say, I've just been put in charge of an outreach program because the head of the department saw my presentation. That 8-minute presentation got her a postdoc, her job, and with her career, just 8 minutes of recording. Brittany got into medical school. R3s, when she walked into the office for a scholarship, they said, we enjoyed your presentation. Put at ease immediately. Jennifer got into vet school, very hard to get into. Dan, who you've seen, got a Goldwater scholarship. We have a Japanese node. We have nodes in Croatia, Japan, the UK, the US, and Spain, okay? This is the most interesting. Saino was in Japan as a postgrad doing research, and she made a recording on the Geoset site in Japan and sent it to India, and she now got the job back there without going back for interview. It was effectively an interview for her. And my colleague Mark Riley sent these links to NSF, and the people there were very impressed. So it's a very good way of conflating something very effective to your research reports, okay? Because you can show your best students, and they're your best advertising. So just put the URL on one of your research reports and click into it. Because nobody reads the reports. You write these things, 50 pages. You haven't got the time to read it when you've written it. Do you think someone's got the time when they're just as busy as you are? But they will click into a 5-minute presentation. Think about it. Okay. Steve, Sam, and Colin and Penny are people working with me on this. I'm going to finish off with one of the biggest puzzles of the century, 20th century. And they're called the diffuse interstellar bands. Diffuse interstellar bands are a set of now about 400 or maybe 500 absorption lines in the visible. When you look at a star, you see these absorption lines. And they're interstellar. They were shown to be interstellar about 1923, proved to be so in the 30s, and I think maybe one has been identified, but none have, and they look molecular. So we've got millions of molecules. We know the spectra, but we've never identified one of these. So what is it? Well, they're called the DIBs, the diffuse interstellar bands. I don't think really, maybe one, possibly aligned. And they're well known. There's no doubt about what frequency, what wavelength they are. Well, what about C60? Carbon's a very abundant element in the universe. We discovered it at the end of the 20th century, about 1985, 1990. And I thought of it always as the third man. And put together a paper, possibly endohedral, but also, if it's around in space, it will have things stuck to it. It'll be a soft landing. It won't be a standard bimolecular collision. It'll be a mattress with easy to stick to it. And the idea here was there would be a charge transfer. Mike Dewar and I put this paper out in 1992. And that would be a very strong transition because it would be about 5 angstroms between the sodium and C60, maybe even more. That's at least 25 times stronger than the average moiety chromophore, okay? At least. And in outer space, I said, well, C60 must be there. It's being pumped. What we didn't know, I thought, well, if we've simulated the conditions in a star and we've got the carbon chains, maybe we've got C60 out itself and this being pumped out. So that was 1992. Now, how many of you know the film The Third Man? Okay, great movie. There was diamond, graphite, and C60, The Third Man. I always thought of C60 as something like Orson Welles in the back streets of Vienna. Shady character. Every time you tried to find him, he disappeared. C60 being the back streets of the galaxy. And here's a bit of film. Harry Lime, Orson Welles, the third man, disappears. And of course, it's one of the most famous films, and that's one of the most famous scenes in the whole of the film repertoire, that he disappears. Anyway, that was my feeling. And then, 2010, the Spitzer infrared telescope, shown here, came up with an amazing result. The white spectrum is from the star, or actually a nebula, and the red is C60 infrared, and the blue is C70. The only recognizable features on this infrared spectrum are C60 and C70. It's unbelievable. We use infrared all the time for identifying molecules and groups in molecules. But out of these particular objects, and about a dozen now detected, the only thing you can see are these strong peaks are C60 and C70. So it's out there. And what's more, it's more stable than any other molecule. Because if it's got something stuck to it, a photon comes in, and it can lose the energy by kicking off whatever's stuck to it. So it's not a standard molecule. It's geodesic. It's the toughest molecule, especially under these conditions, that you can get. Okay? So there you go. It's out there. And you think of it this way. Your carbon atoms came out of a star. That star produced all the carbon. Carbon is produced in stars. Your carbon atoms were once inside a star. That star may have made C60. So you all were once C60. Maybe. Okay. So that's a very exciting thing. Now, turns out there was a film made by the BBC about C60. And here's a clip from it. This is Wolfgang Kretschmer, who with Hoffman did the most beautiful piece of chemistry and extracted C60. And here he is, a friend of mine.
I believe it is there. And it would be rather nice to feel that, in fact, we were on the right track. There are some interesting features in space, and C60 certainly can fit them better than any other proposal that has been made up to now. I'm a believer, and I think ultimately we'll find that it is there.
But others have said that C60 is nothing like a match for the diffuse interstellar bands.
They're wrong.
Thank you very much.
I think we have time for a few questions. Do we have some from the audience?
Stunned silence.
I'm not a chemist, but I'm really...
Well, we all have our problems.
But I'm really intrigued by the spectrum that you showed that we can't explain, and then showing that there's that much C60 out there and nothing else. So could you elaborate that on?
No, there's a lot out there. The diffuse interstellar bands have intrigued spectroscopists and astronomers for 90 years. And when C60 turned up, it struck me, how come it's been around? And we didn't see it until the end of the 20th century, 1985. So it did intrigue me that maybe they were related. After all, they were, with the C60 was detected when the carbon chains were simulated in a star, and it seemed to me that the conditions were, well, that's what we're trying to do. So C60 must be made at the same time, but I didn't think it would be seen so easily by vibrational spectroscopy. I was stupid, you know. I made many big mistakes, and that was one. I was looking for a stronger signal, and we did try that in the UV or something like this, but then by accident they detected these things. So the material has been conjectured. Every spectroscopist, every astronomer interested in molecules has actually proposed something, and we proposed it with C60. And then 92, so 18 years later, C60 was discovered coming out of these stars. And it did, as usual, I thought it would be a small component, but it looks as though it's more intriguing than that. But it's also the best candidate because it's so strong, especially under conditions which would break up other molecules. Because we know the conditions in the solar space, everything will be ionized. Atoms, molecules in these dark clouds are there, with about 400 molecules been detected. But C60 doesn't have a rotational spectrum itself, so you can't detect it by the most sensitive method, which is radio astronomy. So, but infrared came up with the 4 bands. Incredible. Okay. So I think it's as good a possibility as anything else. And my thought was it had to be a strong spectrum, and the charge transfer with something stuck to it. And the fact that C60 will almost certainly have things stuck to it, because it's not like an atom-atom collision where you've got to get rid of with the third body. This can, hit and probably have some very good ways of emitting the excess collisional energy by photons, and by another one going off. Okay, one comes up, another one goes on. So there could be a lot of contenders with sodium, magnesium, calcium, titanium, all the elements. So, and it's very difficult to do that experiment in the lab. We don't know how to do it because it's very cold. Maybe a few degrees Kelvin, and getting it into the gas phase and looking for this particular spectrum is not an easy task. And I don't know how to do it. Working with a friend of mine who's the best in the world at doing this sort of thing, we've still not come up with a good way of checking it in the lab.
So would simulation work?
Pardon?
Would simulation work?
You'll get a result. But I think the actual frequency would be almost impossible to get with the reliability you need. You will always get 400 of these lines. It would certainly worth simulating, but I don't think it would be possible to get the accuracy you will need. I mean, how easy is it to simulate something fairly simple like the spectrum of iron, okay, accurately with those amount of electrons? I don't know, can you simulate the spectrum of sodium accurately? I mean, those would be tests. I mean, the most famous example, which was not a simulation, was the carbon resonance. I don't know whether you know about the carbon resonance. And that was an anthropic one, where Fred Hoyle conjectured that because there's carbon here, there must be a resonance between an excited state of carbon and helium, the triple alpha process. Otherwise, we wouldn't be here. So but that wasn't a simulation. That was a conjecture by looking at ourselves and say, under these conditions, the only way there's enough carbon in the universe to create us, there must be a resonance between an excited nuclear state of carbon-12 and the triple alpha process.
Question in the back.
The magnetic properties?
Magnetic properties.
Yes, they have. Quite a few people have looked at, particularly if you look at Patrick Fowler's name, Fowler, that will be somewhere to look at the magnetic properties.
You mentioned that by shining laser onto a specimen of carbon, you were able to generate carbon C60. I was wondering, why not other carbon formation like 610, 20, 30, and why stop at carbon 70? Why not?
Well, that was the big question. It turns out that 60 is special. And when we showed this, about 2 or 3 weeks later, a friend of mine, in fact, 1 week later, a friend of mine sent me an article by a guy called David Jones. It turned out this guy was a friend, but he was the supervisor of a former student of mine as postdoc. And he sent me this article which indicated something I did not know. From Euler's law, you need 12 pentagons to close up a cage, okay? A sheet of hexagons will not close up. You make a flat floor. And it's a peculiar topological fact. And you need 12 pentagons for closure. And that immediately said, I'm a chemist, and I knew that C60 is the first time you can have 12 pentagons without 2 of the pentagons side by side, because you need 60 atoms. Whereas at 58, you need them side by side. And I'm a chemist, so I knew that 2 pentagons side to side is anti-aromatic and is unstable. And I don't think it's ever been, it's never been made stable. I think it may have been trapped. Pentylene, 2 carbon atoms, 2 pentagons side by side, I think has only been trapped in a matrix at very low temperature. So that was the first clue that it might be special. And then the next, I was still worried because I felt we had to prove it was right, but the major proof for me was I was playing again around with these models, and I thought, well, if C60 is special because all the pentagons are isolated, when can I do that again? So I made 62, added 2, but I had to put 2 pentagons side by side. I was a bit surprised, I wasn't thinking. And 64, I had to put 2 pentagons side by side, and then I clicked, hang on, C70 is a strong feature. I call it Sancho Panza, Don Quixote and Sancho Panza. Or the Lone Ranger and Tonto, I don't know. Anyway, I thought maybe this is really peculiar. Maybe C70 is the second time you can close the cage without the 2 side by side. And I rang up Tom Schmalz and Galveston. I knew they could do these sorts of calculations, and he told me yes, 70 is the second magic number. So it's a sort of dead end. It's a stable compound. And then it does go higher. Everything from 74 we've seen are very much smaller amounts. But C60 is special. But in the gas phase, C32, they grow up. We've shown that you can grow by throwing carbon atoms, carbon diatoms too, at the smaller cages.
Any other questions?
It's a naive question, but since we see the C60 in space,
yeah.
Do we find it naturally on Earth? And if not, why not? Because
No,
we find
not
graphite.
easily. It forms in a sooting flame. In fact, I went to one of the top soot people, and the people who were most negative about C60 were soot people. So I went to one of these guys, visited his lab. He said, come and visit. And I told him, you've got C60 in there. Because the soot people don't look at soot the way that you look at soot in your hearth. What happens in a flame is that the C60 forms in a flame, can form in a flame, and then as it goes through into oxygen, it's hot, and you lose it. So by and large, there is almost none surviving the transfer from where it could be formed in the cooler parts of the flame to, and it's a molecule, so it oxidizes almost immediately. Now, Rick has a paper where it's a little bit in the KT boundary layer. Maybe. I didn't do the experiment, so it's very, very small component. So we didn't see it on Earth, and that's the reason. But the soot people produce that flame, pre-mix with oxygen, and then the soot comes out into a vacuum. And they never put a mass spectrometer over 400 mass units on the flame. They captured only the particles, so they missed C60. If any one of the applied labs had put a mass spectrometer on their flame with more than 400 mass units, they would have discovered C60 in the 60s, easily. Now, Mitsubishi are making C60 by the kilogram by oxidation of methane. So there you go. It's formed commercially by oxidation of methane. It's an interesting story. And again, one that tells you, you know, strategic science will miss things. We'll all miss things. Everything will miss things. But fundamental science will find things that are missed by strategic science. And I think it's another, together with Feynman and Ian McEwan and many other scientists, to say we must continue to fund fundamental science at least the 15 to 20%, somewhere around 15% level. And my worry is now that it's dropped below 10%. And if you drop below about 10%, there's a threshold of the community, you know? You don't have jobs and stuff like that. And I think we're going to lose out. Right? Yes, you can make better transistors. You can make smaller units. But I think the solution of some of the big problems, maybe solar energy, will come from left field, from someone working in a totally different area. And that's probably something that we need to keep stressing to politicians and people all the time. That we need young people who can only do fundamental science. We mustn't squeeze them out of the environment, because there are people like me. I would never, I was offered 5, 7 jobs in industry. I wasn't interested in doing what they wanted to do. I wanted to do what I want to do. And so there are people who, like me, who are getting a problem, and I think it's to the detriment of good science.
Going back to your compelling comments about people like Feynman doing what they found fun and then getting into the real interesting things. And of course, if you generalize it to not doing just what's fun, but at least enjoying it, so it'd be probably, obviously it could work with industry where people, they would be kind of chaotic if we just do, everybody did what they wanted to do. But I guess I'm interested in your comment about by having people, if people are allowed to do what's really fun, do you think in the end that would be, if we weren't allowed to do that, some would think we would lose a lot of the truly original things, and we can get a lot more done if we're enjoying what we do, but somebody's paying us to do it, and we can't do whatever we want. But then possibly, I mean, of course, Feynman and you and yourself, it would come out with things that were just outside the box, so that we would lose the outside the box things without being just what's really, really fun.
I think there's a big problem today. I think R&D, most of it should be done by industry. And universities should have a higher weighting of fundamental science for young people because of disparate. What has happened is like firms like Pfizer, AT&T, Bell Labs, where I was there for a year, have chickened out. They're cowards. They've gone out of this. And they've convinced, certainly in the UK, the government that universities should take up what they are no longer doing. And that is a big problem. And I don't think universities, yes, of course, those in universities who want to set up startups and things like that should do that. But it's not what I want to do. So today, I probably wouldn't be able to get money to do what I wanted to do, what I did. And I think it's important to realize that I was in a special time. In Britain at that time, we had a dual funding system where each department, there were only about 45 chemistry departments in the country. Each one was well supplied with the top of the line equipment. I didn't need a grant to do research. When I arrived, I had nothing. I didn't have any money. I got £5,000 a year from the department for overheads. The students came to work with me with their own money because the government gave each university a certain allocation of quota awards. And the students came to work with me if they wanted to. So I didn't have to pay for the students. For the first 15 to 20 years, I never had a postdoc. All my work was done with graduate students and undergraduates. And in fact, 50% of the projects with undergraduates turned out to be as good as the graduate student because you're less conservative. So it was an environment in which I would have a project for an undergraduate. If it worked, it didn't matter. They picked up osmotically from the lab the technique. But it turned out that's the best thing you do. The best way of doing good stuff is to be non-conservative, to have things on the back burner. Oh, well, I'll do it on a rainy day. And unfortunately, sometimes, because you've got to do something to convince a committee that you're doing something useful. And it's just ridiculous. In Britain, you've got to write 2 pages on what you're going to discover before you've discovered it. You've got to know 3 or 4 pages on the use of what you haven't yet discovered and convince them that it's, well, you do that. And you try and do that, and then you do a piggyback on that, the research you want to do. But the point that I'm making, when I arrived at Sussex, I was able to use equipment. I had a Raman spectrometer, because I've been at Bell Labs in Raman, and a friend, a colleague there, senior colleague, let me use the photoelectron spectrometer. And so I was able to work from the day I started. They gave me a student to work with, and I rebuilt some apparatus. I didn't need a grant. I hadn't got £5,000 a year. Today, kid arrives, they give him $1 million, 5 years, they've got to get an NSF grant, 10% chance per year. They've got to spend half their time writing these research proposals. I was writing them for a microwave spectrometer, and I got it, not in '67, but I got it in 1974. It's a long story. I got it, and the first spectrum on that machine was HC5N, which led to C60. But it was hard getting. I had to go for special equipment, but I was still working. I was still using apparatus. I got NMR papers, photoelectron papers, Raman papers. I was flexible, which you have to be. But I also thought, well, if it doesn't work, after 5 years, I'll get out of this and go into graphics, which is something I felt more comfortable with. And I think the problem today is that tenure-track kids are under so much pressure that it's counterproductive as far as real creativity is concerned. They have to do something important. And what did Feynman say? No importance at all. Okay, just playing. Now, I don't say playing. I don't mean things you enjoy. It's doing something where it's 3 o'clock in the afternoon or 3 o'clock in the morning and you haven't realized that the time is gone. I don't like hard work any more than anybody else. But if you're doing something where you are really tuned in, hard work becomes easy. You understand? And I think that's important. And I really worry about being on strategic initiatives, which is the way that the UK is going, and it's going the way here. There you go.
Please join me. We have one more? Okay, one more.
Thank you. You mentioned a little bit that as scientists, we can be somewhat isolated in a small group from the rest of the population. So what are your thoughts on how important it is for us to explain our research to everyone else, and any strategies maybe you've learned from your online program of sort of the best ways to get that information out and heard by the largest audience?
Absolutely vital. Let me give you one example which I think is close to home. You might have heard of climate change.
Yeah.
Okay. Well, I'm asked because I'm a Nobel Prize winner. I know everything, of course. The day before the Nobel Prize, everybody knew I knew nothing. But today, after, everybody comes to me more or less. Now, on climate change, I do not say there is climate change. What do I say? I say, well, let's look at this. I want you to understand some science. If there is climate change, what might you expect? Go to kids in school. Well, one kid might, well, maybe the temperature rising. Yes, number one. What else? Sea level rise. What about the Antarctic? What's happening there? What about the glaciers? What about the penguins? What about CO2? Talk about all those things and say, well, look, you know, it's a tricky thing, but the temperature does seem to be rising. We do seem to be having much more problematical weather. There's more water vapor in the atmosphere. 1 degree, you can calculate. It's a huge amount of energy, extra energy, even just 1 degree. So maybe that's responsible for some of the hurricanes. And you take those off, and they say, these are the way that science is looking at these things. Each one is very difficult, but it looks as though, you know, that's why scientists think there's a problem. And don't just say there's climate change. Just say, and then they learn how science works. It works by saying this. And I learned this the hard way. When C60 was discovered, I thought we had 6 papers said we were wrong. 6 papers by the major groups in the USA in cluster science. If it had gone to Science, I think that paper would have been turned down. It went to Nature. And there were 2 really quite interesting referees. Said, I don't know whether this is right, but it's a fun paper. It should be published so people... Another one said, yeah, you need to prove it. It's a bit of a conjecture. But there were people with imagination who said, a lot of people will be interested in this. They realized that it was an interesting thing. Then I thought, well, if it's wrong, is it a time of cold fusion? And I thought, well, my career is shot. I really will have to go into graphics. I thought, well, I want to spend 5 years proving it. I want to prove it, but more importantly, if it's not right, I want to be the person who proves it wrong. And I then discovered Euler's law, that 12 pentagons were needed. And then they discovered that C70 was the second magic number. And then Rick's group did some beautiful work by putting atoms on the inside, and the size of what was inside determined the size of these things. And we built up a raft of circumstantial evidence. And then I developed what I call my 4 out of 5 rule. If 4 out of 5, you have an idea, if 4 out of 5 fit, you're almost certainly, accent on almost, certainly right. If only 1 out of 5 fits, you're almost, accent on almost, certainly wrong. And if 4 out of 5 fit, probably the 5th one that doesn't fit, you need to check it because it probably does fit. And so I developed this, what I call my 4 out of 5. And if you use statistics on pretty reasonable sort of error bars, you find that it's 99.99% probable that you're right if 4 out of 5 fits. If only 1 out of it, it's very small. With 5, it goes from like 95 to 99. It really does go. And so that's how science works. You have an observation, you check it, you can repeat it. We could repeat ours. Cold fusion people couldn't repeat their experiment. And then we had 6 or 7 different pieces of circumstantial evidence that say that would not fit if it wasn't C60. We could put an atom on the inside, very stable, and we could put one on the outside that we could knock it off, same atom. So, you know, there was that build-up, which one day, when I discovered C70 had to be the next magic number, I knew that was the day I didn't have to commit suicide, which is a good day, I must admit.
Please join me in thanking Sir Harold. We'd like to present Sir Harry with the plaque that we give to our Wigner lectures. And this one has his name, Harold Kroto, 2015, with the face of Eugene P.
Okay.
Wigner. So now I will hang on to it for you. It's really heavy, so I'll hang on to it for you, but we'll take a picture.
Okay, thank you.
Tilt it forward just a little more.
I would like to end by thanking our organizers, the corporate fellows who organized the lecture today, and also announce that the next Wigner lecture is Siegfried Hecker on April 30th. You're dismissed. Thank you.